Hey guys, and welcome to this presentation on identifying the products of chemical reactions, which is C4.2. So if you're detecting carbon dioxide, what you have to do is pass lime water through it. And if the lime water goes cloudy, then there is carbon dioxide. And that's because what lime water actually is calcium hydroxide. And when you pass carbon dioxide through it, the calcium hydroxide reacts with it to form water and calcium carbonate, which is a white precipitate, and that's what you can see making it turn cloudy. So for chlorine, you just get a piece of blue litmus paper and dampen it, add chlorine. If it turns red then white, the test is positive. It must turn white because that's chlorine bleaching it. If it only turns red, it could be any of the halogens. And then hydrogen, you hold a lighted splint at the edge of the container of gas, and if it makes a squeaky pop, then there's hydrogen. Then oxygen, it's similar, but you need a glowing splint this time. But again, you hold it near the mouth of the container. If it relights, then there's oxygen. So to detect cations, which is positive ions, usually metal ions, one way of doing it is flame tests. Now, flame tests work because when metal ions are heated, energy is transferred to the electrons. So then they move to higher electron shells. And when they move back, they emit radiation, which we see as light. So that's how flame tests work. So you heat up the metal, and then they release radiation, which we see as light in different colours. It's also how fireworks work and how they get like so many different colours. So these are the results of the flame test. Generally, you don't need to know calcium because it's so similar to lithium, and if you're given red, it's always going to be lithium. But the rest are very important to know. So there's also hydroxide precipitate tests, again for cations, metal ions, and you react a compound with a cation in it. For example, for iron, you could do iron sulfate, copper sulfate. And you react it with a metal hydroxide, but usually sodium hydroxide, because that's soluble in water. And then different cations make different coloured precipitates. As you can see, there's a list here. And then zinc and calcium produce the same coloured precipitate, but if you add more sodium hydroxide, the zinc hydroxide dissolves in it to form a colourless solution. So that's one way you can tell them apart. And then if you're detecting anions or negative ions, generally non-metals, there are a few different methods depending on what you're testing for. So for example, sulfate ions, you have to add some hydrochloric acid, then some barium chloride, as it will react to form barium sulfate, which is a white precipitate. So it should turn white if there is sulfate in whatever you're testing. And then to detect carbonate, you add hydrochloric acid because they react together to form carbon dioxide. So then if you bubble it through lime water, it should turn cloudy. So you have to do the carbon dioxide test after that reaction. And if it's positive, then there was carbonate ions. And then for halide ions, you firstly add some nitric acid, then you add some silver nitrate, and then this is chlorine, bromine, and iodine. This is white, cream, and yellow. And you can remember it as milk, cream, butter. There are also instrumental methods of analysis, which rely on a machine to carry out the analysis. And there are three advantages, which is how sensitive the machine is, how accurate it is, and also the speed of it, because it can be a lot faster. So you have gas chromatograms, where each peak represents a substance in the mixture. And the area under the peak shows how much of it there is. So for example, in this mixture, F, there's the most of F, then E, then D, and then B and C, it looks like they're the same, and then there's a tiny amount of A. And then the retention time, which is, as you can see along the x-axis, it's the time taken for the substance to travel through the column. is different for different substances. So that's how you can tell which substance is which. But obviously, there might be two substances with very similar retention times. So it's not necessarily going to be perfect. A mass spectrometer can measure masses of atoms and molecules, and it's often used to analyze different amounts of an isotope. So, for example, you can see if you have carbon, how much of it is carbon-12, how much is carbon-13, carbon-14. And it's also used to analyze different molecular structures. So each peak represents a fragment of the molecule, and the peak on the far right represents the molecular ion, which means the whole molecule. So the mass of the molecular ion peak is equal to the relative formula mass of the molecule. For example, if you had carbon dioxide, that's C, which is 12, and then oxygen 16 times 2. It's got a relative formula mass of 44. So you would expect that far right peak to be on 44. Anyway, thanks for watching, guys. Bye.